about coring. And all the data we gain in the field we store in the computer. We have this ArcGIS database where we save them, and they all have spatial reference. We get the coordinates with GPS and the elevation from the airborne laser scanning data. We can show quickly this first meter. It's quite dry sediment and it's oxidized, and the pH is typically below 4 in this kind of sediment. We can show the measurements from the next section.
But you measure pH directly on this material?
Yes. We also
the dry material? Or?
Yes, we do the pH measurements in 20 centimeters intervals, down to 3 meters depth. And we also take samples in the same intervals, or according to the lithological boundaries. And now we're also beginning to do some diatom analysis for the samples. And, yeah. That goes like yes, you can come closer now. Jo, it's clean. Sorry. Ja.
And the soil profile is also photographed. What? Yes.
I took the camera.
Yeah. This is how we photograph the soil profile. So yes, we take a picture like so, and then it is inputted into the geodatabase. So the picture and all the pH measurements and everything is goes to one big database for all the data. The multi-elemental analysis, the incubation results, and the field pH measurements go directly in there too. So, and if we measure here, it's actually this is actually still kind of high. Yeah.
How long do you hold it for a precise?
So that it could be steady then value.
Yeah. So it depends. I think it depends on the cold weather if the electrode responds more rapidly or not. So
how do you standardize this?
Sorry?
The pH meter. How do you standardize?
We have calibration fluids over there, so we calibrate it every day. Yeah.
Okay.
Yeah. So and and if we look at the black monosulfide sediments, we can see that these are strongly reduced, and the pH rises again and goes over 7. And we have a very strong horizon right here. So these have not yet been oxidized. So, and then we also take Monsel code for colors for all the sediments, and these are a little greenish. Or what do you think, Jeffco?
Yeah.
So, and we also have whole Finland is mapped with airborne geophysics resistivity measurements, which I can show you here. And we use the geophysical data to quite closely check the conductivity, or in this case the resistivity of the sediments, and then and after that we can clearly base our sampling points from that data. And as we can see here, well, we have an area which is strongly impacted by acid sulfate soils. And the geophysical borders, whoops, well, okay, this is quite nice. Quite rapidly respond to this. So we can see right in this area we have a strong anomaly in the conductivity, and all of this area is acid sulfate soils. And the same goes for this area too. We have a strong anomaly in geophysics.
What kind of sample densities do you do?
It's normally something like one sample per 2 square kilometers.
Okay.
Yeah, but it depends on the area.
Okay.
And if the geology says that there is high possibility to find acid sulfate, so then we make more observations.
When we look closely at one of these areas.
So how well is that correlating with the geophysical data?
Quite well, actually, in some places. So it depends. We have tried to make some models of areas that have not been mapped by hand, but it's usually when you come closer to the littorine sea shoreline when it doesn't correlate that good. But in most